PhD students defending their research work in the same week and expected to graduate in the same year. This is great for us as department, school, and also College of Natural Sciences. I'll just give you a brief about public defense. This is quite new in this university. A few years ago, we used not to have this kind of public defense where the public is invited to listen to the findings of the PhD research. But this is just a new development in this university, and we find it very interesting. Now, of course, it wasn't quite easy to come up with how this kind of operation is going to go. And in this process, we appoint a discussant for this defense. The discussant, or sometimes we call, we use the word opponent, but this is actually discussant. This is the name agreed upon now in the proceedings in the university. The student who is going to defend his PhD thesis is Denis OKELLO, and the title of his thesis is Rock-Bed Stove Suitable for Solar Cookers with Thermal Energy Storage Systems. Denis OKELLO has been doing this research for the last 3 years or so, and he's ready to defend his research work in this public defense. Ladies and gentlemen, allow me also read to you the roles of a discussant in this public defense. We expect that the discussant will engage the PhD candidate in a very constructive scholarly manner and discuss the merits and demerits of the entire piece of work, chapter by chapter, provide a scientific and scholarly appraisal and a critique of the candidate's work. The discussant is also expected to ask pertinent questions in respect to the text. Ladies and gentlemen, allow me also to inform you that for this public defense, we are privileged to have appointed Professor OKELLO as a discussant. I'll give you a brief about Professor OKELLO. Professor OKELLO got his BSc degree from the University of East Africa in 1970. Got his master's in 1973, the University of Alberta. PhD in New South Wales in 1979. His area of specialization is solid-state physics, material sciences. He has been employed in Makerere University since 1973, and he has supervised many MSc and PhD students. He has also he worked as a visiting scientist, Tokyo Institute of Technology for 6 months in 1986, International Center for Theoretical Physics, TST 9 months in 1993, and has acted as external examiner in many universities in the region and beyond. His research experience, his research areas are in materials, thin films, clays, ceramics, electronics, and instrumentation, science, and technical education. He has attended many workshops, presented papers, published many academic papers in different journals. Professor OKELLO has won a number of awards. He won the Denis Award Research Fellowship University of New South Wales. This is between 1976 and 1979, while doing his PhD. He won a Matsman International Foundation Fellowship Research Award in Japan in 1986. He won a CERAC visiting scientist at ICT PhD Italy in the late 80s and early 90s. He's a member of the American Ceramic Society and Materials Science Africa Region Chapter. Professor Kawa, you are most welcome to act as a discussant in these public events. Before we proceed, I also need to give you guidance on how we are going to proceed. We are going to give time to Denis OKELLO, approximately 40 minutes, to present the panelists, the public, your research findings. And we expect minimum interference, but well, the panelists can ask one or two questions, but they will have their chance later on. After the presentation by Denis OKELLO, I will request the discussant to engage the student, chapter by chapter, probably page by page, from the beginning to the end. And the discussant, that process is going to take approximately the same time, probably around 40 minutes. In this case, the discussant will engage the student and keep pausing to allow the student to answer. But if the discussant prefers to go on up the end and the student answers later, that is up to the discussant. After the discussant has engaged the student, we will then give a chance to the panelists to ask questions. And that will take not more than 15 minutes. After the student has responded to the questions of the panelists, we will open it up to the public for another 15 minutes. And the public will have a chance to ask questions. After the public has asked the questions, we will request the public to move out, and then we do the teaching hour with the student. And the student will also move out at a later stage, and we do the teaching hour as directed by the policy. Thank you very much, ladies and gentlemen. We are sorry we are starting a few minutes late, but unless you have some questions asked, I take this opportunity to invite the student to present his research findings, the panelists and the public. Thank you very much.
Thank you. My research work is based on exactly on the based of the solar and climate college, and we shall look at the potential for using such solar system in Uganda. I'm Denis OKELLO. This research is provided by Professor Banda from Makerere University and Professor Uganda process engineering from there. Now, my research will be divided into we shall look at the introduction, something brief of the literature review, then the method used in this study. We shall look at the results and discussion, and finally, we shall look at the conclusion. Now, on the introduction, after we're looking at the energy consumption in Uganda, we find that over 80% of the energy used for cooking, supplied by wood fuel. And with the high annual population growth rate that estimated at 3.2, that implies that more pressure is being exerted on the natural forage as the demand for more energy increases. So, in addition to that, according to the recent report from the World Energy Council, it indicated that actually more than a quarter of the world's population do not have access to commercial fuel. So that is whether there is need for alternative energy to be used. And in developed countries, mainly the energy supplied by fossil fuel resources. And these fossil fuel resources are got its associated effects. They are commonly linked to the global warming, the increased carbon dioxide emission. And in addition to this, these sources are actually limited. In some time to come, they will be limited. So that means you cannot rely on fossil fuel forever. Now, when you look at the sun is basically the most abundant source of energy. And it is estimated that the annual energy reaching the earth is over 7,500 times the world annual primary energy consumption, which is currently estimated at about 450 exajoules. But before this energy can be tapped, there's need to know the information on how this energy is distributed in a particular region. That information is required in designing the solar energy system. Now, solar energy basically offers an alternative solution, the current energy demand, and this energy can be used for both domestic and industrial application. And specifically, the use of solar thermal systems, which finds application mainly in solar water heating, solar drying, solar cooking, and space heating. That one can really improve on the standard of living of many people. Now, the use of solar addition to cook have got several advantages. One of the advantages is that, especially in the rural village, cooking is done by women and many children, and they're always forced to move long distance to search for wood fuel. In addition, the use of wood fuel also produces a lot of smoke. So if you get an alternative system, then that will be able to improve the standard of living of most of those people. Now, varieties of solar cookers actually exist, and they are being used in different parts of common in Asia and in some parts of Africa. But these cookers still need some improvement if they're really to be widely accepted. Because solar energy is available in an intermittent way, and it fluctuates so much that this system cannot be used for cooking continuously. These solar cookers are only able to use them during the certain period of the day. And so in order time to make this system competitive enough, if they're to be accepted by the majority of people, the system should really be able to cook at any time of the day. The cooking should not only be restricted at the beginning of the sun period. Then, the cooking should be indoors. Of course, nobody will really like to go and stand in the sun and do the cooking, and the cooking rate should be fast enough. Now, for this reason, there is need for now development of thermal energy storage, which can be incorporated with these solar cookers, and it will really make this system competitive with the conventional electric and gas cookers. Now, in another trend to solve such, Professor Lapses from University from NTNU has proposed the development and construction of an air-based solar cooker with a thermal energy storage. Now, thermal energy can be stored using basically three mechanisms. Can use sensible heat, phase-change material, and chemical reaction. The first two are really more developed. A lot of research has been done on the sensible heat storage and phase-change material. But these are going to be done for low temperature applications. Commonly used for space heating applications. Now, some of the criteria used for selecting a storage medium include the thermal capacity of the material. In addition, you need to know the temperature range of your material, the temperature range of application will guide you in choosing the type of material you should take there, and the safety of the material and cost. I always take into consideration when choosing a thermal energy storage. And for this reason, air systems using raw gas thermal energy storage has actually been used successfully in low temperature application, mainly for space heating. Now, but if you are to use this one at high temperature, you remove it from low to medium or high temperature application that is suitable for most cooking application. There is need to know the thermal behavior of this rock bed. Now, the statement of the problem. Currently, this lack of information on the distribution of the daily amount of solar radiation and the monthly average hourly direct solar radiation in Uganda. Because this information of the daily amount, the distribution of the daily amount, it helps in sizing the storage. The storage size such that, you know, if today I have solar radiation, if I don't have it tomorrow, I should be able to maybe, if I have a big storage, the storage should be able to take me through the day with low solar radiation. And the monthly average hourly direct solar radiation distribution help in actually estimating the backup energy sources you will need in some month to low radiation. And most existing solar cooking systems that are available, they only work during the sun periods of the day. Now, in order to make them applicable during periods of low radiations, there is need for a thermal energy storage. So the thermal energy storage will make the solar cookers enough with conventional electric and gas cookers. So the objectives of this study, the main objective is basically to develop and test an air-based rock-based thermal energy storage unit for solar cookers. The specific objectives: one is to model the distribution of the daily amount of solar radiation in Uganda. Develop a model of spatial and temporal distribution of the solar radiation in Uganda. Then we need to validate and modify one these commands model for an air-based system with an experimental result, and perform energy analysis of an air-based rock-based thermal energy storage with different checking and scaling methods. Optimize the storage size of an air-based rock-based thermal energy storage, and experimentally compare existing pressure drop correlations. Now, a brief literature on different solar cookers. That picture above shows actually a panel-type solar cooker that is currently being promoted in Uganda by some NGO known as Live Views Eat. So that picture was taken from India, where they are trying to promote that panel-type of cooker. But that system has got a lot of disadvantages that you can only live there and use in the sunny part of the day. The design is also, you also restricted to different types of the cooking vessels that can be used to such kind of system. And it's basically, it cannot be used for big family sizes. So that is why it's not really being picking up so much. The other design that is well documented in the literature is on the solar box cooker. The solar box cooker, the advantage of this cooker is that it can use both direct and diffuse radiation. And this design is basically just showing this is a solar box cooker, and this is another design with the same surface area. But if you construct like this with additional reflector here, you're able to get a high stagnation temperature, the maximum temperature is on 7 degrees to 160 compared to 130. So this is basically showing that you can improve the performance of solar cookers by adding additional reflectors at the sides. Now, another direct solar system here. This system has the advantage you can use with the high temperature. But the disadvantage with it is that cooking is done outdoors. You have to stand in the sun to do your cooking. You should be able to wear sunglasses to protect your eyes from mineral solar radiation that are reflected from here. And you cannot use it during flight periods. Only during the sunny part, that's where you want to concentrate the radiation to the focus. And another disadvantage of it is that you need to continue tracking the system to follow the daily motion of the sun as you go. Now, in order to achieve this is the design that is proposed by Professor Lafset, that consists of an energy collection unit and an energy storage. Where in this case, you have your concentrator. This concentrator may be installed, may be put on the roof, which concentrate this heat to your absorber. You can use a fan to blow this, to extract this heat and take it and store it in the position. And then you can use it at any time of the day. So this research is actually being sponsored by the National Responsible for Radiation, and it involves a total of 6 universities. So different components of these systems are being tested by different universities. So for our case, we're looking at the behavior of the storage, how the storage will actually behave. And there's a study by Makerere. Before that, if you concentrate solar beam using a parabolic dish on a small receiver, you can make temperature you can up to 700 degrees. So that temperature is really good enough to do most of the requirements requiring high temperature. Now, other designs of solar box cooker is this one that is imported by Maria Telpes in the US, where this system, this solar box cooker, we reported that it was able to bring its calculation temperature up to 231 degrees Celsius. And other tests that were performed using solar box cookers was actually to see how you can improve the efficiency of the cooking by changing the design of the cooking vessel. Where in this case, we have added some things have been attached to this cooking vessel. And when they compare the performance of these two cooking vessels, this one was perform 7% more efficient, or 7% more efficient than the first one. And other design of solar box cooker that I reported in the future includes one down there. Now, our study is mainly based on the sensible. We're looking at the sensible heat storage. And in sensible heat storage, we're saying it is basically stored by raising the temperature of the material. And it's extracted in the reverse process. During cooling, you can extract the heat from the system. Now, the advantage of sensible heat storage is that they are really cheaper. And they usually have larger thermal conductivities compared to the use of phase change materials. Rocks, the use of rocks, basically, rocks are readily available and heat can be transferred using here as a heat transfer. As a heat transfer fluid, they are actually compatible with the air-based system. That's why we decided to go for it. And the main disadvantage of this sensible heat storage system is their low heat capacity. Their thermal capacity is relatively low compared to PCM. That means if you use the PCM, if you use the sensible heat storage, you may need a bigger volume to store this given amount of energy compared to the same amount of energy stored using the phase change material. Now, From here, if you look at the most important column here is the thermal capacitance, which is the product of the heat capacity and the specific heat capacity. This thermal capacity, if you compare the thermal capacity to different materials, you find that actually this cast iron has got the highest thermal capacity. And that really would be typical material that can be used for storage because they have the high thermal capacity. But other factors, like you need to take into other factors like the cost of the material before you go to select that. And for our case, we decided to go for this rock, so the stone, this granite stone. They are commonly available and they're relatively cheap. And the thermal capacity, though is low, but still comparable to some of these other materials. So, let's look at the methodology. The methodology used in this case, this is divided into mainly three sections. The first one is on the method used in modeling of solar radiation. In this case, we use solar radiation measurements that were obtained from the meteorological stations and some that were being recorded by the Department of Physics. And the distribution in daily amount of sunshine were analyzed and compared using the running average method. We compared using the 2 days and 3 days running average. And the monthly average daily direct solar radiations were determined using a modified Armstrong type correlation that is reading, that was developed in Uganda. Now, we estimated, the method we used to estimate the monthly average hour direct solar radiations was the method that was given by Horowitz and Makerere. There's a model that can be used to estimate the average radiation from the daily values. Now, the solar radiation stations that we used were actually distributed in these climatic zones. We have this like the Lake Victoria zone, the Ankole southern zone, then we have the western zone, and actually Choga zone. The Kampala zone we never had in the station to consider. So these are the stations that we considered in modeling the spatial distribution in solar radiation in Uganda. Now, in modeling of rock bed changing temperature profiles, we use a modified Schumann 1D model. In this model is modified to account for the existence of temperature gradient within the stones, accounting for heat loss to the ambient and the thermophysical properties of air was taken into account. And this is the model that describes the behavior of the fluid and of the solid as hot air moves through the rock storage. Now, the schematic of the model is basically where we discretize the bed in end sections, and hot air is basically reduced from the top. In that case, you'll be able to know the incoming temperature. I'm using now the formulas from both the solid and the liquid from the previous slide. You will determine the next temperature for the next section. Now, the method which we used the experimental method used to analyze the rock bed storage, we shall look at that actually, how we constructed the rock bed storage, then the construction of the pressure drop. And in this study, an attempt was made to see how we can use phase change material in an air system. So we used some phase change material that were enclosed in some copper tubes. We shall look at it, and the cooking, the design we used for cooking. Now, during the construction, from the literature review, we found that actually the heat loss basically high at relatively high temperature. So in this case, an attempt was made to create a vacuum storage. So we consider actually two cylinders. We had 2 cylinders, and we inserted some deflecting materials in between the space, in between the space, in between this individual storage. 3 of these materials were actually wrapped around to reduce the heat loss by radiation. And here we place some 4 thermocouples. We have actually placed some 4 thermocouples on the outer surface of the cylinder to monitor the performance of the evacuated space. This is the design showing the base of the container, the support for the rocks. And this is the design we use to position the thermocouples at long distance along this long storage. Because the inner radius is 30 centimeters and the length, the length is 1 meter. So to position the thermocouples at long distance, we use that copper pipe. And this is how the top part of the storage was actually looking. These are the thermocouples that are coming out from this, inserted in. And the system was actually sealed using a silicone sealant to keep it airtight. Now, the general schematic of the rock bed system is that in this case, you have air from a compressed air tank. This air is metered before you determine the flow rate before it flows through the heater. So it's heated and you introduce hot air from the top. As it flows down, it heats up the rocks and it exits from the base. We had thermocouples that were placed at no distance, and these thermocouples were connected to the data log that was interfaced with the computer. And we were measuring this data every minute. Now, to compare the performance of two different storage, we consider actually a short and long storage. This is a long storage with a diameter that is important. This is we look at the situation where we have very short storage. How that behave in such kind of system. Now, the use of PCM, the copper PCM tube that we use 4 PCM tubes. There's another test that we performed where we inserted 4 copper tubes into the rock bed. And the PCM material was used here was actually a mixture of sodium nitrate and potassium nitrate in the ratio of 60:40. And this system has detected the melting point at about 220 degrees. Now, the design that we use to determine the pressure drop, the pressure drop is actually these, and these are the different types of rocks which we, the different samples which we consider in, we study the pressure drop approach. The pressure drop was actually made to consider this tube, the internal diameter was 18.6 centimeters, and the measuring the pressure tap were placed at a length of 1.8 meters. This is where we put the pressure tap, we pick the pressure screw, and this was connected to the arm of the manometer, which is the manometer. It's actually not very clear in the function here. So from there you see the rise, the pressure drop at different flow rates. Now, after storing this heat in your bed, how do we extract this heat? Can we use this heat really for cooking? So an attempt was actually made to use this thing for cooking, where we modified the top of the storage by this is the top. We added some aluminium fins. We attached it to the plate to increase the surface area, increase the area for convection, in order to improve on the performance of the system. And this is how the top part was actually looking. And this is now the design during the discharging, using it for boiling water. What we tested was just basically boiling water. Because you see most foods actually, most foods are meant to perform by boiling, except for frying, you need the temperature of about 180 degrees. But when it's a temperature of 100 and up, you're going to blow. So in this case, we reverse the flow of the air. In this case, you are blowing air from the down, and it was coming from up, and this one is just showing how water was going. Now, the schematic of that system, we modify it. After modifying, this is basically the arrangement of the thermocouples, and this is actually how the top part is actually looking. Now, we look at the results and discussion. The result, basically on the daily sunshine values that we have obtained from different meteorological stations, we considered a total of 10 stations in this case, which have got the sunshine measuring equipment installed. We tried to arrange these stations according to the climatic zones in which they were really lying, and closer stations we really try to put them together. Now this one, we have more stations in the western region, and the western region we decided actually to put it alone. But these other stations, other regions have only one station, we decided to just put this one for Victoria, and then for the southern zone, and actually southern zone. Now, from here you see actually that relatively higher monthly sunshine values are recorded in Soroti. The red one I've got relatively higher sunshine values, and relatively low values are experienced around July from that study. And when you look at the western zone, this is basically what you expect. You must see the actual have relatively higher value compared to some of these other stations which were considered there. And another analysis that was done on the daily and the running average distribution. In this case, we consider the daily values, where we have daily sunshine hours together. And if you plot if you take the 10th percentile and the 58th percentile and the 98th percentile of the daily distribution, this is the blue line is basically showing the distribution for the day. Now, if you consider 2 days in a row, and you perform that statistical analysis with the 10th percentile and the 15th percentile, and interesting features you see here that in the 10th percentile for the 2 days, it's really an improvement in the value of sunshine hours, which is indeed that the actual days, if you have days, days with low radiation are supposed to be followed by days with higher radiation. That's where we talk about give an improvement in the daily values. And similar analysis you can see from other stations like Ginger, Kasese, and Bala. These are the values that are recorded from there. And for Soroti, actually, relatively higher radiation, so it's higher values. It's obtained from that page. If you see the 10th percentile in the day, the 10th percentile value for the daily distribution, unfortunately, very high values. Above actually the minimum just occurring on the left, but other values are actually from 4 hours and above, showing better improvement in that station. Better performance if you put a surveillance system. Now, the spatial distribution in the area amount in the monthly average direct solar radiation is basically, this is how we moving from one station to another. We try to put stations which are within the same climatic zone together, and in moving from one climatic zone to another, we move the stations which are nearby are actually placed together as we move from one zone to another. And these values are in kilowatts hour per meter square per day. And you see that actually relatively more radiation is received in the month of February, and Lira, Soroti, and Tororo relatively have got relatively higher values in this month compared to stations like Kabale, Mbara, and even Kampala have got relatively low values of incidence radiation as you can see from that. Then, this is the temporal distribution that was obtained from the monthly average value. So this is how you get how solar radiation will be approximately distributed with the monthly average value of the direct solar radiation. In this case, you have a relatively low value in this adaptation. Then you have radiation going up around 700 watts per meter squared, and more radiation occurs in the month of February compared to other months. And the same considered for Soroti and Lira, relatively high radiation in Soroti, and Lira, you can see now the special distribution. The yearly temporal distribution. Now, the results for modeling solar radiation using the Schumann 1D model. This is how the bed will be charging at different time of a different charging time. The parameters used here, you use the parameter from the bed, and it's actually summarizing the thesis. This is how the bed will be charged after different time. Or, as you continue, after 1 hour, you find a bed where this is the length of the bed from 0 up to 9. After 1 hour, you just find just the first top 10 centimeters peak have got some I've received some temperature. But as you change the continuous, then the heat goes down the bed. Now, we compared the Schumann model with the experiment. Now, when comparing the Schumann model with the experiment, this is what the model is giving us, and this is what we're getting from the experiment. The dotted lines are the experimental results. So, here, what you see is basically that after 2 hours, there's really the model is really approximately closer to the experiment, but relatively lower. There's a discrepancy at the base, where you find the experiment giving relatively higher values compared to the model. This was basically because the model which we considered, we took into account the temperature gathered within the stones, while the experiment made the assumption that both the stones and the fluid are the same temperature. So, what the experiment was basically doing is the air temperature as it is goes down the bed. And after 3 hours, there's this discrepancy between the model and we see that the experiment is going to be giving lower values compared to the model. This is basically due to the assumption that in the model, with the related heat flow by conduction. But from here, this is basically that in addition to that, the heat is being conducted from the higher temperature in the top down to the base, in addition to the convectional flow. Now, in an attempt to see the performance of this solar radiation distribution in different parts of the country, we compared the solar radiation data performance in Soroti and Mbara, and this is the distribution you get. This you get for Soroti. That is obtained from the previous slide from the temporal distribution which we have seen for Soroti and Mbara. And in this case, we consider what you consider relatively lower radiations is received in Mbara with a peak at about 400 milligrams speaking at about 750. And we just consider the radiation distribution for the month of February and see that if you have this storage in Uganda and this month, how will it behave? Now, using the parameters of the concentrator from the textbook, you'll find that if you have the same storage size in Mbarara and Soroti, this is how the storage will behave. You have the more radiation in Soroti compared to Mbarara. So the solicitation definitely will perform better because of the more radiation. Now we look at the experimental results that were obtained from rock bed terminal storage. Under this, we look at the effect of inlet temperature, airflow rates, particle size, and the charging temperature profile. And we shall also look at the results of thermal degradation when you have both a short and long bed, how the heat will behave if the storage is kept for some time. Then look at the pressure drop results. Then you look at the results for having both rocks and PCM together, the comparison. Then the cooling test and the cooking test of a heat bed of rock. Now, the effect of inlet temperature, if you keep the airflow rate constant and just change the inlet temperature, increase if you fix the inlet temperature at about say 300 degrees, this is how the profile will behave. Okay, we are not able, this one was fixed at 300, but we're not able to complete the 300 because of the losses that are involved between the heat and the top of the storage. So if you fix it at 300 and you fix it at 400, this is the behavior. What you see, if you keep the flow rate constant, you see that both graphs are of course similar profiles. But they have similar profiles, Kelvin profiles. But the only thing you see that if you look at the energy stored, basically more energy, find that during the more energy stored at high temperature compared to lower temperature as a function of time. And the results of the effect of airflow rate as this airflow through the day was performed by doubling the airflow rate, which this one was the airflow rate of 2.4. Grams per second, and this is for airflow rate of 4.8 grams per second. Now, if you double the airflow rate, if you look at this profile, it's a different profile. If you look at the profile, this is the profile after 2 hours. The profile after 2 hours is similar to the profile after 1 hour of charging when you double the airflow rate. This profile after 1 hour, because in this case the airflow rate is more compared to that. So basically what you see that basically doubling the airflow rate or increasing the airflow rate to increase the rate of charging of the bed. And we also look at the effect of particle size. If you have large stones and small stones, in this case we consider stones of approximate diameter of 35 millimeter and 14.6 millimeter. If this is the charging profile you get for the two different stones. For the smaller stones, this is the profile we actually have. And there's actually more specification when you have smaller stones. Because the stratification is the measure of the difference between the incoming temperature and the temperature at the base. So you find that the bed is more stratified in a bed consisting of small size stones compared to these large stones here. This is mainly because with small size stones we have very small void, and therefore here I've got a lot of time that meaning a bigger surface, a bigger time of interacting with the stone. So they will not move very fast through the bed compared to the large size stones. Then the thermal degradation test, we consider a bed which is highly stratified. If you charge a bed that has the profile you have after 10 hours and after 14 hours. So basically this is showing that if you store if you store this in this profile, after 14 hours you will get those this heat, the top part heat that will be is not getting what is the high temperature that you need in that case. And a similar test was performed in a short bed, a bed of length about 40 centimeters, and this is there. A similar profile that was observed there. So it's actually observed in this short bed. You see this a dynamic actually. Some temperature area, and interesting area actually carry down the middle of the bed where the top part is dropping while the upper part is increasing. Then another test was performed in checking what we're referring to as a preheated bed. Like if you charge your bed today, you don't use it, it will be bed up to this point. And if the following day you don't want to use it and the summer radiation you want to add it more, this is the kind of profile you will experience, the bed will experience. You'll find that actually, as you charge this top part, this is the top part, that is only the top section that will be really getting more energy, and when you reach here, you'll be able to. In a one-to-one system, this heat is actually blown and will actually be blown out. So, more of the charging will occur at the topmost section of the bed. Now, if you have a bed which is less stratified, where the difference between the top and the bottom actually small, small compared to the previous slide you've seen. And this bed, when the bed is just like this and you leave it for some time, this is the profile that was actually that you'll be able to see. After 2 hours, 6 hours, 12 hours, and 18 hours, this is what you'll be able to get. And this is basically showing that there's actually more heat loss from the bed in this system, because we try to insulate it, but our vacuum system never works. So there's actually a lot of heat loss from the bed. Then the results of pressure drop. The results of pressure drop were compared with the correlations that are available in literature. This one, we have the damper correlation, the Egmont and the Chandra. This is the experiment like that, and this is the Holland correlation. This damper correlation, it correlates pressure drop as a function of airflow, speed, and the particle size, particle diameter. But it neglects the effect of void fraction, the void fraction of the bed. The Chandra correlation consider the effect of void fraction on the pressure drop, and the other correlation was developed for very washed rocks. And it also consider the effect of void fraction on the pressure drop. Now, if you see this one is for small stones. The result for small stones, you see that this one, the pressure, the correlation by able actually is very much close to our experiment. And if you look at the damper correlation, is slightly above. It's slightly higher compared to all this. This is for a 14.6 millimeter rock. This is the result made for a 18 millimeter rock. This is the kind of behavior. You'll find that now. This correlation is actually begins underestimating the pressure drop. And for a 30 millimeter rock, this is the correlation you get. But this one is still higher there. And for a 35 millimeter rock, this is the equilibrium you get. So in this case, we recommend the use of actually the damper correlation to estimate our thing, because it does not, first of all, it does not overestimate the pressure drop, and it does not take into consideration the effect of the void fraction, because void fraction is a function of packing. Now, the behavior of a bed, the results of the behavior of a bed that is containing rocks only, because we're comparing both rocks and this. We have a bed of rocks only, this is the changing profile that you have. And if you have a bed with rocks plus PCM, if you use rocks and PCM tube, this is the behavior. You find that Actually, the use of the cooperative was just a short circuit the bed. There is actually loss of stratification, more loss of stratification in the bed compared to the other results. And the degradation, if you look at the degradation in a bed of rock solid and a bed of PCM, this is the degradation profile which we have seen earlier, and this is the degradation profile if you have rock and copper PCM change. You find that after some time, the temperature in the bed will equalize actually faster if you have those, if you put copper tubes in the storage. And the charging efficiency. Charging efficiency basically a measure of the stratification. And efficiency close to 1 means that the bed is really more stratified. And if you see in this case, if you have all the rocks here, and rocks and PCM, you find that actually incorporating those copper tubes containing PCM decreases the stratification. It's actually faster loss in stratification in that bed compared to the on the rock. And we perform some research on the cooking, using this bed for cooking, where we reverse the floor and put some volume of water on top of the storage. And this is the profile of the heating of water, the blue line. While the other profiles are keeping the temperature at different base sections. We started with 12 liters of water. You can use 12 liters of water with a flow rate of 0.049 kg per second. This water took 53 minutes actually to begin boiling. Now, we kept the flow rate constant and we continue just adding a liter of water each. And this was actually the heating of water. That was actually a different time. And longer heating occurred actually as the top temperature was falling faster. And this final one, when the bed temperature, with the top part temperature is actually falling about 130. This water is just set to the maximum temperature of 98 degrees Celsius. Now, another cooking test was performed on a bed that was almost fully charged. This one was performed by charging the bed and leaving it. The bed was left for like 30 minutes for it to stabilize. Then we just put 3 liters of water on the top without initiating any flow. And this was the heating curve that the water is on top of. Without any flow, just put it on top of the storage. This is the heating curve. It reached almost a constant temperature. This is the top part of the bed, and this is the temperature. Other section dipped into the bed. This is the temperature that we are experiencing. And after here, when the flow rate was initiated, when you put the flow rate of 2 grams per second, this water was supposed to boil after 28 minutes. And this is now how the top, after initiating the flow from the bottom, this is now the top part temperature started to rise up to there. But at this point, we increase the flow rate and we are adding a liter of water each, and this was the heating curve. The heating curve of water every time a liter of water was added. So this test was kind of like if you have your bed like now, you cook with it, and you don't want to use that energy. And you don't want to cook at the end, you really cook. You cover the bed and you leave it to stabilize for some time, to stay. This is the profile that we'll experience. How it will degrade. This is the profile after that cooking, how the temperature from the top was moving. It was actually the most constant temperature after about 6 degrees Celsius. Now, this bed, after 13 hours, before another test, before it upgraded to the temperature of 20 degrees the top part, and it was having this kind of profile. Now, after that, we performed another test, another cooking test, like if you want to cook now the following days. We put here 2 liters of water with the flow rate of this. This is the heating curve we get. It's 253 minutes here for it to boil. Then At this point, that one was overlocked, then we put another 3 liter. At that same constant, at the weight. Here, we started with 7 liters. 7 liters with a flow rate of 0.019 in the first part. And it was able to go into 53 minutes. And when we vary the flow rate, we reduce the flow rate to 0.59 and put in 1 3 liter. This is the heating current. Now, then after boiling, then we try the test where we just shift a small flow. Small flow and see how the water is going. This is the curve. A very small flow is this negative flow rate, just 20. This is the heating curve. We heat it up and we almost a constant temperature. So here we increase the flow rate, and this is the heating curve as a function of different temperature properties. Now, the conclusion from here that we see that solar radiation is distributed over the year with higher potential in some periods. Locations at relatively higher latitude receive more radiation from what we have seen, and it is not common to have 2 or more days in a row with relatively low sunshine or no sunshine. And we have found that the modified small model can be used to predict the charging temperature properties of an air base, energy storage, increasing inlet temperature increases the inlet content of the bed, but the profiles are similar. The charging properties are similar. The bed changes faster with faster flow rate, and small size particles promote stratification by pressure. Pressure drop should be taken into consideration. The degradation is formed to be much faster in the high temperature region. Then the dampness correlation can really be used to estimate the pressure drop. And the use of PCM can enhance the energy content of the bed, but stratification is actually reduces stratification in that case. And rock stock can be used for cooking in the same way as electric and gas cooker, where just increase the flow rate, the cooking rate can be controlled by gas, including the air flow rate. And the recommendations would that they still need for more solar installation in order to allow and improve functional evaporation. We need to promote solar thermal systems in Uganda, especially solar cookers. There is need to design and test thin films for heat extraction in the recirculating system. If the recirculation system is good for that, then there is more studies needed on the thermal insulation. Since there's a lot of heat loss that we have seen. And the design of PCM container with fins that can enhance the melting rate need to be taken into consideration. And at this point of time, I would like to thank Mr. Supervisors. It's abundant to that for their guidance and discussion. We're looking for the financial support. It is possible for you to go through Norway to do some of this experiment. The staff from the Department of Physics that have really been helping, a lot during the seminar. The friends from the new small-scale solar projects are really acknowledged for their input when this part of this work was presented during our workshop. The Makerere University staff development for granting the tuition waiver, which may be possible. I want to thank the technical staff both at NTNU and Makerere for helping me in the construction, and my family and friends.
Yeah, thank you very much. And we just proceed to the way we have arranged the work. So at this moment in time, allow me to invite this person, Professor Denis OKELLO. He can environment that we want to engage the students, but probably just as a hint, you can either go through the work, discuss, then the student respond afterwards, or you engage the student page by page, chapter by chapter. That will give you time to respond.
The Dean, I'd like to thank the Dean for his warm introduction and supervisors, fellow colleagues. I'd like to thank Mr. Denis OKELLO for the work that he has done. I was requested to respond as indicated and discussed. As the Dean said, this is a new thing we have been doing for a short time, so our experiences are not as much, especially our colleagues from Norway have done this before, and we borrowed the idea from them. And Charles says, it looks a good idea. So when you see me, I'll be learning together with all of you in this kind of discussion. And so I thought I would prepare some slides. Now the Dean has suggested that I can either go through the discussion up to the end and the candidate response, or I can take the time and then response. Probably I'll try to see, take a couple of slides, and then he might respond. If we see how that one goes, if it goes okay, we shall continue that way. If it doesn't, then I will just go through, and then he responds at the end. And I will follow the way he has presented his work, but with less details, because he has given us most of the details. I will indicate which focus I will spend more time as we go along. And therefore, I will not spend much on the background and the problem statement and the objectives. But let us see how we proceed. I shall proceed with the introduction with points on the solar energy conversion. The candidates discussed trends, the energy needs, and energy use, which is quite common to all of us, and mainly for domestic use and industrial use. We are all familiar. But the problem is that the conversion. He has stressed in the thesis two main areas. One is photovoltaic, and the other is the thermal heating systems. The photovoltaic, we are familiar. University use for lighting and sunlight applications. I have discussed that in some detail, but greater detail has been given in thermal heating systems, especially solar cookers. We have to have done this slide so that people don't read below. But as I said, this is the learning experience. And in particular, the solar concentrators, the parabolic ones, both the dish and the cylindrical ones. That's the merits, the solar box cookers. But he has not really given us a background in some direct use, which are obvious. Some of these obvious things people overlook them, but I think they give us a hint on what is needed. For example, I just with passing, sunbathing. I know in Europe is a very good practice. Some of them come to the tropics for sunbathing in the sun can. And there is one particular application in sunbathing, the sonars. Sonars are for physical fit houses. We have not mentioned that. And a number of people are not fit. Probably with sonar, they will do a good practice. And you can even make money you may want to use solar heaters to circulate steam in the gyms and other places. So that is something you may want to tell us why you overlooked that. Secondly, crop drying is a common practice in the tropics, especially in the so-called third world countries. And it is as important as cooking. His emphasis has been on cooking. But crop drying is quite a problem. We can't just consider agricultural people design crop dryers. When we were growing up, we dried coffee. Moisture content is a very important consideration in storage. So probably he could have mentioned that as one of the uses of direct use. And of course, timber drying. Professor Msazi has tried to design a timber curing system. Uses direct solar, but with air flows, air differentials would be a great help. So probably you mentioned something why you mentioned that. I thought we would have come out in the way of the introduction. Then the other one, since we are dealing with solar energy, I thought solar energy spectrum would have been a good thing to give in the introduction. Because it is not really given anywhere in the discussion. We just give that we are taken direct into solar energy. But the spectrum is a good thing to look at. And one thing I thought one would want to mention in the solar spectrum, this is common knowledge, the visible range is very narrow in here. But one point I thought we would mention is that the selective absorption systems which we are familiar, or not familiar, but we know there are some selective absorption systems. One in particular you may want to remind the candidate is the chlorophyll pigments and the carotene pigments applications in plants. They select for the manufacture of energy. And the solar spectrum will indicate these absorption, the chlorophyll and the carotene. There are about 3 types. The lipids, there is one here, there is another one here, and some other bacteria. The purpose of mentioning this is that probably we may want to store solar energy by selective absorption. And we never know some materials. They do it, Professor Titi knows, for lighting, for window buildings and cars. The glass, the greenhouse effect, the greenhouses, they do selective absorption and they retain the energy. So why not select the energy we want to use? Maybe such systems would also have been mentioned in passing. So probably they may want to tell us why you overlooked that the solar spectrum is on the review. I'll mention a few things here. They have given us most of the information, and we talked much about the solar irrigation and modeling. In particular, his main discussion was the sunshine cover, and of course we know for us in the tropics, sunshine everywhere, but varying in distribution. And the point about this radiation, probably would have said a little bit more, is the cloud cover. I know it is discussing these radiations, but the cloud cover and dust cover is rarely mentioned. But if you, for us here in Uganda, during the dry season, the December, January, February months, we get dust from the Sahara because of the air wind flows. You get dust cover. And of course, in the drier areas, dust cover is an important factor. It can be hazy. We are all familiar with the dry seasons here and the dust cover. It does not mention that. And it would be nice, especially when we think of the energy considering Soroti. If you went to probably Karamoja, the drier areas, the hazy will become a factor. And of course, the night hours, that we are familiar with. And then the The other point is that in this radiation discussion for the literature, the direct solar radiation instruments, he has told us the average, the data is mentioned for monthly averages. Of course, he didn't mention the daily in some of the data. But I was wondering why not weekly or bi-weekly averages? I don't know. The monthly averages are preferred in most of the data. The previous workers whom we gave reference to, they give monthly averages and the plots. But why not? What is the reason? You can divide the periods in many other lengths you choose. And then I have indicated there that there is, well, of course, I discussed diffuse and solar irradiance. I'm not going to say much about that, but you can tell us about the choice of the averages and the periods. And then in the models, he has used the diffuse fractions, and he has taken those systems, the root mean, square error, and the mean bias error. I did not mention them in the discussion here, but they are discussed in the thesis as the type of models to use. He has also discussed in the thesis the tool, the neural network, and the neural network. He has said developed it, but actually those authors used it, and maybe that is something consider, especially this, that the artificial neural network is a powerful tool, was developed to, I think, from the medicine point of view, the neural system in the human body, and now many people use it. You may want to say a little bit more about how you can use it. It's just mentioned, but the other two are the ones he has used mainly. And then, of course, in the discussions in the literature review, he has pointed out some relationships. Those relationships are expressed in one is named representation at full length for the stratified characteristics of the energy and the temperature down the bedrock. But there are some he has used in the solar energy distribution, like that one. The symbols are not clearly defined. I don't know whether he understands them himself. Probably will tell us some of those relationships, whether he does understand what they mean. And of course, there are other considerations. One particular one I was interested in was the radiation balance. He could have said a little bit more in this radiation balance, because you get the radiation, you get reflections from a number of sources. For example, scattered in the atmosphere, but also from the earth back, and there are many other influences to that radiation. You could have said a little bit more. Then, of course, there is evaporation and convection exchange processes. So this would be mentioned in passing, not as detail, but it's part of the radiation, which add up the direct and indirect, and probably in the solar collectors, they may not discriminate what they are collecting. Maybe more direct is more obvious, but even the other components may be accepted. So mentioning them would not do any harm. And then the solar thermal systems for cooking, many have been discussed. I think that's okay. I'll say a little bit more on that when we come to the other sections later. But there are some simple cases we could have mentioned in the literature. This because of the setting of the work in the tropics, and especially in Uganda. So he can tell us, maybe he's not aware, but probably he is. Direct open vessel heating is a common practice. The majority of our people in the rural setting, we do direct open vessel cooking and drying. I've already mentioned rock drying, clothes drying. Most of us, when we wash, we don't have dryers here. We just put them outside. It's direct applications. And then also, you could have said open fire cooking is a common practice. Now, those of you are visiting, when you go to Uganda, you will see this open fire cooking, roasting. That is not mentioned. Probably one will improve with this kind of methods. Under fire roasting, probably some of you are not aware, but we do under fire roasting. If you travel to our area, in his area, you stop over at a cafe, you get some cassava, very well done. Yeah, some of it is open fire, others is under. Anywhere, yeah, growing up, you go to dig, as you burn the grass, you put some of the things under the fire, and you get it cooked. So, they are elementary, but I think they are good to tell us what we can do. So, and in the review, this would be done. And of course, the fuel, I don't have to say much. We have already discussed that. But also, you could mention some of the other sources. And then also, in this review, the bedrock has been fully discussed. Although I would like to say that in the write-up, the TES, thermal energy storage, in some cases was thermal energy system. So that needs to be corrected. If it is storage, then, but in my, it was thermal energy system, and then you were, in the write-up was TES systems. So if it was storage, then it should be storage. I thought that was a repetition. If it is storage, that may be correct, but otherwise, I sort of not much to say here. But you know, the bedrock has been fully discussed, and some mention has been made with limestones, which looked attractive, but of course we know limestone, carbon rocks, you have the risk of dissociation with carbon dioxide and calcium carbon oxide. So, but he could have mentioned it why it is not used because of it has a very low, it can dissociate at very low temperatures, so it will not be as attractive. And but also, in one thing you could also have mentioned is local practices. Local practices in storage. They are not very efficient, but they are there. You can mention them. For example, especially in this central area, when you cook matoke, you wrap them in banana leaves, and if you want to keep it warm, you keep it, you wrap it in more leaves and put it under fire. You cover with ash. It will stay warm the following day and eat it as good as, well, Professor Wood probably knows. But also, there are other, in the rural setting, there are underground bakeries. You dig hole and put fire, you make stoves underground. And they store heat. So probably these could be investigated in the review. You never know, you could adopt some of these. So while the bedrock is attractive, but there are also local practices. In fact, when we come to insulators, for example, people transport banana, cocoa especially, in wet banana fibers. Even milk, you wrap it in banana fibers, wet. It keeps very good insulated. We do like a refrigerator. So, but that's another story for our discussion later. And see on the review, sorry, this section is a bit long. Probably I will stop and then we will respond. There are some chemical processes I was also mentioned. For example, you mentioned reversible reactions. That one is okay, but you know, energy must be supplied. Probably, and that point was not made. You must supply energy, but also there are other reactions like exothermic. I think some of you did chemistry. Ammonium chloride is a popular one. Yeah, there are these exothermic reactions. They give heat. So probably one could mention, maybe you can store these reactions when they react, they give you heat. Yes, those are not mentioned. Water was mentioned, the dissociation of water, right, like the symbol, the numbers are small. But, you know, when you mention water, the storage of the gas and the pressure involved are problems. And probably you have mentioned that why water may be used for dissociation, it may not be as simple and give reasons. And then finally, insulation. The insulation, possible insulations. Here, in the discussions, in these presentations, you don't mention, but in passing in the thesis, you will see two fiberglass and rock wool. Rock wool is not defined. Most of us are familiar with the fiberglass, but rock wool should be defined. Probably you tell us what it is. And some other insulators, why they are not used like asbestos, used to be common to use as an insulator. It's not mentioned. Why not, for example? And then, since we are like clays, you should have mentioned the possible use of these other local insulators because we use them. The temperatures we are dealing with are not very high temperatures. They are cooking temperatures between 100, 300, 400. But sand and clay are used in kilns. In the charcoal stoves, Professor Peter again is an expert in this. Charcoal stoves, the lining is clay. One would want to see they are used as insulators. Why not? These are easy, they are cheap, and probably the temperatures we are dealing with are not very hard, but even if they were, they are used in furnaces, ceramics. Those are not mentioned as possible alternatives, and why not? So probably you can tell us. Now, Mr. Dean, maybe I stop here in response to that. When this review is still fresh.
I don't know whether you are halfway. If you are halfway, probably go up there.
I think we can see the house. It appears there for the consensus of the week.
Yes.
Now, what do I sit down?
Yeah, thank you, Professor, for those. I don't know if I can respond using those slides. Will the slides from?
Yeah, we can use mine, of course. It's no reference.
Yeah, in this first part, you asked me why we have not actually mentioned the direct other uses of solar radiation. The case is actually mentioned that this solar thermal system you can use it for cooking, space heating, crop drying, etc. So this other ones will be captured around. They can be they already captured. Now, next we talk of the solar spectrum, showing actually the different spectrum of the radiation. As I mentioned actually earlier, that this research is actually divided. We are talking of the solar energy and the solar concentrated system within storage. It's divided among different participants. Okay? The spectrum actually here was really not so much related to energy storage in this case. So I decided actually to put that on there. But it's a good point. Okay, this is talking about the spectrum. Then, yes, here the reason why we choose actually, why we decided to use sunshine, why we left out the issue of cloud cover and dust cover. Here we're just trying to see, because the sunshine hours are actually measured using this camera stock sunshine recorder, which reduces actually the sunshine if the direct radiation is actually available. It's able to concentrate it with focus and it will be able to burn that piece of paper. Since we are looking at concentrating solar energy system, concentrating solar energy are only able to work when the sun is available. So that's why there's really some correlation between sunshine durations and the application of concentrating solar energy system. That means the time that we call it sunshine duration, that's when you can use the concentrating system. And the use of weekly data, the use of daily and monthly data. Why not weekly or bi-weekly? That's basically because we want to look at the yearly performance in different months. That's the average. How different months will really perform if we use this system different periods of the year. There's a correction there of the artificial neural network that was reported by Professor Banda and Bureau in the paper. I think that was an error to be corrected by the not developed. Now, this relationship you see here is basically a relationship that was used by somebody in India to estimate the daily beam radiation received in India. That's actually page 14 from this page. The symbols there actually they are well explained. Where HB is basically talking about the beam radiation, average daily beam radiation. Average monthly beam radiation in that case. And H naught, the H naught is basically extraterrestrial radiation. B naught is a constant here. And in this case, we are missing the constant A naught that is commonly given from the Page equation or the Armstrong equation. The reason given there is basically that there is basically no beam radiation when there is no sunshine. So that's why A naught is eliminated from this formula, and the symbol basically are called single unit from the Page equation. So that was just noted from the another study that was given there. Then the radiation balance. The radiation balance was not really factory. No, Frika performed the studies of different types of rocks and actually found in this paper found that limestone was actually separating, while rocks like granite, basalts were able to withstand temperatures up to 300. We saw that was actually the basis. Other practice of using local materials. Applications of this so they can really be, you can use it for cooking, or it can also be applied to even for generating steam. It can also have other applications. Once you have the energy, you are able to get the heat there, then you will use it for many other applications. Then we talked about the reversible chemical reaction and why we said ammonium chloride is not mentioned. Well, I'm not going to the literature that was actually related to that. Probably, maybe because of some other factors that are really considered here. You need to consider the cost of the system, the safety, it may be poisonous at some temperature. So those are, it's not reported here. But the use of water, is really commonly available, it's really cheap. It's cheap, and that is why I think the studies actually find You see how you can usually differentiate what is this components of hydrogen and oxygen and store the two separately. Because it actually indicated here that at room temperature, if you bring hydrogen and oxygen together, they will not react in the absence of a catalyst. So one, there's a catalyst where that reaction is possible. So I think it is possible to keep them. The insulation, the use of rock wool and fiberglass is actually recommended for high temperature. They can perform better at high temperature because they have relatively what is low thermal conductivity values compared to sand and clay. Actually, there were some studies that were done on the use of possible local materials like ash, clay, charcoal dust, and the value of the thermal.
They should be mentioned then in the writer.
Their values are actually relatively high for this item application. Because if you're looking at a material which has a thermal conductivity, say about 0.5, and you're comparing with the rocks which have also got very low thermal conductivity, say about 2, then at high temperature, the material will not really be able to, there will still be a lot of heat losses. As we have seen, even those other materials which have relatively low thermal conductivity, they will still be there. We still also have quite a substantial heat loss. I think it's...
Yeah, that's mine. Okay, thank you very much. The purpose of mentioning this was that we mentioned and the good reasons why we are not using. Those points are not mentioned. There are possibilities. I'm not so sure about the thermal conductivities, but one can always take them up. And the next, probably I'll take the next batch and come to the end. Otherwise, time is running. The methodology and the results and discussions we shall take them together. And well, the methodology is straightforward. The sunshine parameters for solar radiation distribution indicated, and the stations were also discussed, and how to keep the energy, the TS, and design and construction, and all those have been well discussed in the thesis and also in the presentation. However, I thought one could point out something to note. One, the temperature of the rocks and air, well, it's assumed equilibrium is attained after some time. And it is not as directly clear as this equilibrium. You know, somehow equilibrium is a bit tricky, especially when you have both solids and fluids. So probably a strong case must be made that there is equilibrium. For how long? We were given the temperature profiles for charging and discharging and degradation, but the equilibrium part is not, between the two is not discussed. Then the other one is the actual volume and shape of the rock pieces, and then find the averages. In the thesis, there is, the volume is determined by having a chunk, number of rocks in a container, and then you add water filling, and then to find the ratios. But probably one may wish to point out the rocks. When you pick this from the quarry, there are all sorts of shapes. And usually, the dimensions used are diameters, but they are far from spherical. If you had picked them from the seabed or the showers, those which are round, they are not elliptical, they are not even round, they are elliptical, then the soil will be different. But if from the quarry, they are all sorts of shapes. So probably you need to pick a sample and describe the volume and then take the averages. And that was not clear, in my opinion. It can tell us how you got those average diameters and why you did not take individual sampling find the shapes, and then find the averages. And secondly, I just had it, but it's not clear in the thesis the type of rocks. You mentioned in the presentation about granite. Granite, even describing them, what are they? What is their composition? You see, these are geologist terms, granite rocks. But for an average person, you may not know. Why choose granite? Why not quartz? Quartz are the white ones. Those of you have been to building sites. You see the stones they use. The most common one for the road making are the gray type. Those are the granite. But the white ones are normally quartz. What's the difference between granite and quartz, or a mix of the two? Why not? You mentioned that iron, cast iron has the highest capacity. Why not use these brown rocks? Because they are very common. You know, brown rocks they crumble. You have seen brown rocks. They are softer. But why not use them? Because they have highest iron content. So the type of rocks, be more specific, and probably mention and why it was granite as opposed to other types. Probably you tell us why that is so. Still in methodology, the system has been discussed, blowing hot air. There were two methods, from top to bottom and from bottom to top. But one thing needs to take into account that the diffusion process is in a porous medium. Now, your porous medium is not a straightforward porous medium because we hope the channels are joined, are interconnected. But in some porous materials, the channels stop at some points and then you get new ones. So, but probably your system is a little easier. The channels are continuous. Maybe you should tell us why did you mention some of the diffusion processes in a porous medium? For example, there are fixed laws of diffusion. They are not mentioned, but probably you do not want to consider those. But it will be something considered later research. And the other things were, what am I saying here? Capacity ratios, charging efficiency, and heat loss. Now, those capacity ratios, you are given, like the formula given, stored energy and stored energy maximum, is given in the thesis. Those in the discussion, we do not say much about it. But there was one particular question which interested me. Energy expended in pumping the system. You see, you pump the system, but you are not told us anywhere, even when you consider the efficiency of the system, because you must supply energy to pump. And is it worth? One may ask, is it worth to pump? Whether you are pumping from top to bottom or from bottom to top to extract the energy. So probably you are spending more energy by using a pump. You don't know. And maybe you will tell us why the pumps have got capacity. They are low power pumps, but this must be a low power pump. The other country could have used a suction pump, they use the chemistry, maybe it would be cheaper, but then you have to have a liquid flowing. So suction pumps are also common. If you don't tell us even the type of pump you are using, probably use the bicycle pump, we don't know. Yes, so that the system is complete. You see, you have got the pumping system, the heating system. Where were you drawing the air from? Was it just air from the neighborhood? You could have got an air chamber, we don't know. But that's something you can tell us. And then, of course, your work was done in an indoor system. Where probably the reason you gave was that because cooking is indoor cooking, maybe that's okay. An outside one was not necessary. So maybe you can overlook that other question. And so now you keep those in mind. Then we can go to the results and the discussion. I'm going to run through these briefly. The solar radiation distribution, the results were discussed with average sunshine hours and global and direct solar radiation. Those we have done. But to repeat these, some other factors which you mentioned in concluding this section of solar radiation distribution is one, the rain distribution. Just mention it because it affects, you may be in the process of of doing your energy collection and just rains. And in the tropics, there are various types of rain distributions and rainfalls. The most common around here are convection. We just hear rains here, doesn't rain in town. Most of those are convection or rains, leaf rains. So you should mention that. Then the other one you do not mention is altitude. You have mentioned latitude. Probably that is obvious. As you move further away from the equator, the sunshine like in the northern part is a bit more higher than going to the equator. But also the altitude is very important to mention. You did not mention why some areas which are quite important, like Procedural valley areas, where there are no stations yet. Probably I mentioned that, but they are important because of the altitude. The sunshine hours there are much reduced. But even here, why here? Because we are into raising. So that point probably will tell us why altitude is not considered. Then the other parts, Kasese has a station, but we did not mention its location in terms of relief. It's in the Rift Valley. And there are some areas in the Rift Valley, Kasese and Tiago is one of them. And there the temperatures are much higher because they are much lower. So that factor of altitude comes in important. Please mention it in your results for discussion, those other areas. And then the other one, elsewhere, as I said, those are as expected. And there was one point I put down, probably I might mention it here, but in the results for discussion, the western part is represented by Mbaraga and Kabale. But probably that should be called southwestern, where Masini is also mentioned. Yeah, midwestern. But there is a big jump in the north, where there are no stations there, but should be mentioned. I think West Nile region is not considered. So probably south and midwestern would be preferred rather than saying western in terms of regions. If you consider population, West Nile is not a big population. West Nile and Karamoja, those are big areas. But I thought I should use conclusions this way. And then the results, we continue with the results. We have discussed the rock bed, the TES modeling in detail, you have seen that. But in the comparison of results with the experiment and the theoretical modeling, there are 3 sets, hours, 1, 2, 3. I don't know why you did not take the 4 and 5 and 6. There is the results are presented on page 99. There is a graph there. I think you saw it, but you may not remember, but it is there. So the fitting is quite good, but why did you leave out the other higher hour? Probably those are more interesting. The higher, because you want longer hour storage. Then the charging temperatures, profiles, energy distribution, and interpretations, those are also discussed. I have already talked about the rock sizes, but I bring it back here that in the presentations and the work done, 2 rock sizes were taken, and I suppose as averages, the small ones and the big ones. And then he makes some conclusions that the small ones are better. Later you remember. But you see, on 2 is not a very good physics conclusion. You need a little more. Unless you give a reason why those 2 sizes. Of course, the reason is given the smaller ones are better than the other ones. Okay, but you must give reason why only those 2 sizes. So what about if I use the sun? They are much smaller, but they also perform the same way. There must be an optimum value for the sizes. And this mainly depends on the diffusion processes for the heat flow. And that point must be captured for those sizes. And then, of course, we have already discussed the insulation, the rock wool and fiberglass were used. I already mentioned the local materials as given reason for the temperatures, although I'm not so really convinced about, I'm not sure, I don't know the thermal capacity of the rock wool and fiberglass. It says they were 0.2. Thermal conductivity, I don't know if they are 0.2 or less. Probably Professor Pan remembers the thermal conductivity of clay. We have done clays, the thermal conductivity is the resistivity that we don't gas. But you need to compare and give reason why the clays cannot be as good. The temperature, that's not a big deal because you go to Kadans for brickworks, they use lining the refractory bricks are made of ceramics. Refractory bricks will be cheaper than fiberglass. And the high temperatures, they are much higher than the cooking actually. The firing temperatures 800 to 1200. So the temperatures are much higher. These clays can be porcelain in furnaces. So the temperature is not a good reason for the clays. They are much better. Fiberglass was used in ovens in the old, I think it's probably still used. It's a kind of fiberglass, so therefore you use more heat. But it could be mentioned. Yeah, it should be mentioned. Okay, that we continue with the observance and discussion. And then the other point is the charging, preheated, we have discussed that. And the temperature rise from observation is on the top, and similar for degradation. What I would like the to tell us is the explanation. One should give explanation. At least we know one of the possibilities is the temperature gradient, as expected. But that's not clear. It is implementation that the observation and the temperature rise. So probably you want to tell us some of the physics underlying those temperature rises. And then the pressure drop in the rock. He has given the numerical expression. I think it is numerical supported. This is parabolic relation. The rate of mass flow with closing constants. We have discussed that at length. And I think also in the presentation. But again, the two sizes of the rocks come in to affect the pressure. So one should, well, probably our mechanism should come under here when you are about these pressure, to mention them at least, so that you can convince us those air flows. And then, as we draw towards the end, the thermal energy content, and this brings us to the introduction of these phase changing materials that the thermal energy content is enhanced. The physics behind it is not clear why these phase changing materials. Probably a little bit reason they want they need to be given. And secondly, the choice is the nitrates. Why nitrates? There are no other material. Why the choice of nitrates should be taken? And probably, I don't know the association temperatures. Nitrates they fix nitrogen in the ground for agriculture. They do other things. Probably you may want to tell us why nitrates. There are no other materials. Are they cheap? You will tell us something about them. And then, of course, they are better conductors, as widely said. And their behavior is as expected because in such good conductors, they will transfer the heat much faster, and the degradation will be faster with copper rods, for example, and the charging efficiency will be also probably better. So that one is expected, but the choice of materials probably is important. and charging efficiency is also indicated and is referred to as transient. I don't know, probably you should tell us why that choice of transient description is preferred, and the rest of the discussions in the results is as presented, so I'm not going to repeat myself. You can mark those other questions. And then the last comment on the results is the heat extraction. You notice in the presentation, a boiling water was used, and quite indicated boiling enhanced by airflow from the top or bottom. But I was wondering, testing your system with water, why wouldn't you take rice? Rice is the easiest thing to cook. Maybe, yeah, it would have been much interesting. You put rice, and you cook and you eat. Of course, beans are a little harder, but you could have taken fresh beans. Now, one thing about cooking, you see, slow cooking is preferred for the nutrients to biological system to take place. But sometimes, slow cooking with some foods, they don't cook. For example, matoke. You need much heat at the start and then reduce. What do you call it? When the food is half cooked because of initial heat being too low. I don't know the English word. So you need to mention that the cooking process is that the cooking process is. So you need much heat to start with and then reduce. Slow cooking gives, that's why microwave cooking is not as good for testing. It's really good for warming, but not good for testing. So you should mention the cooking mechanisms would be good for you to understand and processes. And then give us a little why you chose water. Water is everywhere, but the real thing to test would be rice, which is easier, and steel, fresh beans, or anything else you choose. Then I would be convinced that the system is going to work. So probably you know you have the reasons. And finally, I repeat this, how much energy is used at the end to blow into the air. Probably you need to calculate. The pump will have specifications. When you know the rate of pumping and the amount of just the rate of pumping and the specifications of the pumping system will give you the energy input. And then you can subtract, and see the total energy input and how much you get out of your system. It will be good to have an efficiency which balances out. You know, in physics you can never create or destroy energy. So you simply change. Sometimes you decide which change you want to prefer. You set out with a number of objectives, and at the end of the day, you want to see if those objectives have been achieved. I would like you to go through those objectives. You told us the conclusions, but in my readings through your thesis, one was modeling the distribution in the daily solar radiation, spatial, and temporal as part of your objectives. Well, you did use data from those stations to do that, and the typical kind of modeling that was done. So, as I say, only the typical observations are made. Really, there is no real model you have proposed, but probably can convince me that there is. But from it was the results which you gave the trend, and the model was were reduced, and but not a new one from the results. The Schumann's model is validated and indicated that was okay, and then your air-based broad-based thermal energy, as we said, was storage, not system, as presented. So that was also okay. Now, optimize the storage side. That one is only on two sizes. I have said that already. That was part of the objectives, but probably you may need to check on the two sizes. You cannot here give an optimum. You may need a little more, but you can convince us. There is no reason. And then, again, the pressure correlation is again similarly located. So those were some of your objectives which we set out to achieve. And in my opinion, you have achieved the right number, but they beat. So in conclusion, I would like to say that the solar radiation distribution in Uganda using data from a number of stations have been done, but northwest and mountainous areas are not covered. And there are other considerations that affect solar radiation, as those he has tried to explain, but not their main concern, but probably mentioning them in the review will be okay. The thermal energy system, that was how I got the system, but now he says it's storage. So I can take to storage. Using a rock bed indoors has been analyzed. I think promising results which one can use. And the testing has been done with water, as we saw from the presentation, but a little bit better has been done. And then the overall efficiency, as I have already indicated, probably you can tell us whether you can find it or not. And I would like to thank you very much.
Yes, Dennis, we're going to request that you try to speak straight to the point, because we need time for other sections of the public comments. So if you can leave in 5 minutes, that would be wonderful.
Thank you. I just want to go very fast through them.
I'm starting with methodology.
Yeah, the methodology. The reason why we're showing the air temperature basically between the equilibrium and the rocks, we're considering the rock to be relatively small, where, okay, that's just an assumption using the Schumann's model. And if you have a small rock, they should be having uniform temperature distributed quite large rocks. Then the shape of the rocks, these rocks will actually obtained from the quarry. We just got them and wash them, and they will actually require this variable shape. But the method we use is actually the method that was used by John Lynch. Some publisher called John to see from the literature review. He used a similar method for determining the equivalent particle lines in that case. But there is a book called Duffy and Beckman. This shape, the shape of rock, actually is a very complicated system to determine. So there are those are just approximation methods to approximate the diameter. Then the description of granite, why we decided to the description of granite is missing here. That one I'll be able to add that. We also talked about the use of other brownstones. So these are brownstones. Mainly that one depends on the temperature. I have not tested it, but using other studies that was reported in literature, we decided to choose on the granite because they are very common. Some of this information that we obtained from the Department of Geology. The diffusion process in the diffusion process in the bed is something we mainly consider. We never consider light because in this case we're using force conversion to charge the bed. So that was we never consider that in our analysis. We need to think about it. Then the pumping power that we require. There's actually a relationship between pumping power and how pumping power is related to the flow rate and the pressure drop of a given material. The pumping power is basically giving us the flow rate over the density times the pressure drop. So if you know the pressure drop and the flow rate, you can determine the pumping power that is required to use the pump the air through the bed. Then there is something on rain distribution, which are the rain distribution was actually given from the map that we got. The map in Uganda, the Uganda rain is divided into 4 main regions. Where you have the Victoria region, which has got more rainfall. You see actually from that map, all those the rainfall distribution within that those regions are given. Then the altitude, if they are really missing, I thought I had them, if they are missing, I mean, they need to go straight from what I have in the book. I think it will be but I thought I had them all the stations. And now the reason why some stations like Procedural and Makerere were never considered is because we never had any stations around there. We left them out. Now, the temperature profiles for invalidating the temperature profiles of what they just consider non-temperature. The reason because we already got the shapes, we have been considered for even other temperatures, but the distribution of the factory was we already obtained with that, and we decided just to keep it there. The rock sizes, why we just compare to the two sizes. The rock sizes mainly in this case is very important when considering the pumping power, the pressure drop across the bed. You see that smaller rocks have got really higher pressure drop compared to the rocks. So in this case, we just look at two extreme sizes. Now, the optimum size will really come from the simulation, where the sample is determining actually the optimum. From the simulation can be the optimum size. That will not require too much pumping power at the same time, will not also will be able to achieve some boost of vibration within the bed. The insulation, we already talked about that. Then charging a preheated bed. Let me go to the slide which we had for preheated bed. Yes, this is there. This is the profile. If you have a bed that is already charged and we've been adding heat to it. Okay? Actually, what is happening here? What is happening if you use hot air for me? The top part of the bed begins to heat up. And this thing is heat up and which is at the middle here. Both the air and the rocks are actually almost at the same temperature. So there is no absorption of air from heat from the air anymore here. So the temperature remains constant until when there is a difference between the temperature of the rock and that of the air. That's when you see that the profile begins to increase again. So when here at this point the temperature of air and rocks are actually they are the same at the same temperature. So
and that, sorry, so you need to give that explanation here that at the top, the temperature differences are higher than when the hot air is nearly the same temperature as in the middle. So you need
I thought I have, but it's not that great for adding that explanation. The pressure drop will really give this relationship here because when you compare them with other existing relations, all other existing relations are written in this form. They're related by this, that kind of relationship. And for the pressure drop, we really consider all the rock sizes. All 4 rock sizes were considered. That's when we came to the conclusion that what smaller rocks actually have got really higher pressure drop compared to relatively smaller rock. Now, on the use of PCM, why we use nitrate? Because of their melting temperature. The melting temperature is actually within the range, the temperature range for our application. The melting temperature of this is at about 220. It's a table that I presented. The temperature is 220 for the nitrate mixture. And we use copper tube because copper is basically a good conductor. Because heating of this PCM is mainly by conduction of heat from the rocks and the surrounding air through the copper plates. Now the charging and transient efficiency, why we refer to this as transient efficiency? Because charging has to charge the plate basically in changing time. The proper is changing. And so we commonly refer to as transient charging efficiency. Now we look at the boiling test, the reason why we never tested it, why it's so big. If you read through the methodology, it indicated very well that most of these stuff are really cooked to the boiling. If you're able to achieve you're able to achieve the boiling point, then you will be able to cook. So that's why we left that one. But basically, no, I'm not an experienced So, the questions of the efficiency of the system, how much energy is used to grow the hair? The energy that is used to grow the hair can be determined from the expression for power that is related to the flow rate and the pressure drop. That is indicated earlier, but they're probably missing that. For this one, if not the flow rate, the pressure drop, so that's not the power. And the density of the material, you can determine the power requirement. The efficiency in our system, for this system, will never terminate because this is the first case we decided to run. So you blow the hair. And in this case, there's happened a lot of losses. Where hot hair, you blow it to the top, and it's actually part of it is used at the top of cooking and others are just smoke this around. But for efficient system, you need to think of a recirculating system where this blow is not here, it goes through the top and you recirculate it so that that energy is not lost. And that way you achieve a much better efficiency. But for this one, we're just trying to show that it's basically possible to use it for cooking, but we are not saying it's enough. If you have to cook it, you use that same efficiency.
Our contention is that it would be nice to consider those things as we go along, so that at every stage we have got a measure of possible use and give reason. Just say it is possible. Of course it is possible. Yeah, but some reason must be given. And then you can say, well, it is possible, but not so yet. Then you can also get an indication of how you can improve. But without a numerical estimate of the efficiency, you don't have a driving desire to improve.
Yeah, thank you. I'll give you some of that. Then the objectives, basically was modeling the distribution in the day, solar radiation, and looking at the spatial and temporal distribution of these stations. The distribution, basically the daily amount of solar radiation. See, this one was dictated the kind of data we had. We had only this daily sunshine duration. So for those stations, that's what we look at. We use the method of the random average. But the spatial and the temporal distribution, we also had only very few stations as we saw from the map. And we tried to interpolate actually between those stations to move from one station to another. That was the result that was given in the map. The schema formula that was validated, that is okay. An error system. air-based system, what we represented. Now, optimizing the storage size. In optimizing the storage size here, we are looking at the possibility of in optimizing the storage size. Actually, this is why we already thought of incorporating the storage size. We're looking at actually the size of the storage, not just the size of the storage material. Optimizing the size of the storage here, we're looking at how we can have a smaller system that can really perform like, I mean, if you have a system of on the rock and a system with rocks plus PCM, that's why we consider incorporating PCM material into the rock-based storage. So in that, you see that if you use that PCM material in the bed of rock, you'll be able to store more energy compared to when you have on the rock. And in that case, that would reduce on the size of the storage.
At that point, maybe you want to make it clear. There were two things. One was the size of the system. There was a big size and a small size in terms of height. You showed us, remember you saw the two. So in that case, optimization is a bit tricky when you are having one system big, one system short. That was my question. The other one was on rock sizing that we already talked about. That goes together with the pressure correlations. But probably continue.
Thank you. The pressure correlations, that one we said we actually consider for the four samples. The conclusions, this suggestion is actually very okay. Acceleration and distribution in Uganda using data flow, the number of stations we need to integrate that. Other stations are actually missing.
That's a very explained fancy.
Interested, I think I'll explain the overall efficiency. I think that's the
Yeah, thank you very much. Ladies and gentlemen, this completes the session for discussion who was engaged students. Thanks very much for that exercise. Thanks, Denis. Now, next we give the opportunity to the panelists to ask some questions. And this should not last more than 2 minutes. Thank you very much. You're welcome. Professor.
Thank you, Leon. Thank you, Mr. OKELLO, for the presentation. I had quite a number of issues that I will take on the main list. I mean, to be my English, in some cases, talk of lack of information. I don't think you mean that you need insufficient information. And something that has to make you so that who can best. One that has, when I look at it, has like sort of cooling things. And you say that one was more efficient than the other. I thought when you have the larger surface area, the energy loss will be more. So maybe you explain to us the physics behind it. And the other thing comes, I've been wondering, if I look at this figure 4.1 line between the radiation data, Masindi, Assessor, Mbarara, Kampala, and even figure 4.2, where was this study done? What is the relevance of that in your study? Because you are not using those data, you didn't use this there. So why do you present the results? And there are quite a number of those. Maybe explain. And the other thing I was wondering, you introduce the hot air from the top. Suppose you introduce from the bottom, because hot air rises hence rise. So I thought that would be easy. And maybe we just pass this. I've been trying actually to link the soil condition data that you have, the solar cooker and the soil. The link doesn't come up very clearly to our performance.
Thank you very much for that. Yes.
Thank you, Professor Chichi. Thank you for your correction of lack of information and change. That's just misusing words. Now, for the cooking surface, what you are saying.
Plus 1 so 2.
This?
No. You are 2. What 1 substance? Yes.
Yeah.
You say the one with the one who says more efficient than the other.
Yeah. Okay. Let me begin with this one very fast. This is I always insert in what? In a solar box oven. You have it in the oven, that means you don't minimize it for storage. But you are looking at how much you can make the heat inside. This is already a transparent glass cover for the oven. Okay. Then figure 4.
No, okay. I've not understood. Because this is one case you put the one on the left. Okay? And in that case you put the one on the right. You see, when you put the one on the right, it's more efficient.
I see this is more efficient compared to this.
Yes, why?
Why? This is behind it. Look at this. I have this oven. I put in this one box cooker. Okay? This one has got a smaller surface area compared to this to absorb heat that will go inside the cooker. And for this case, I have a bigger surface area. In that case, the temperature inside will be more than what we get with that.
Why am I asking? You see those things the same way, like
these are things.
Cooling. So which means they lose heat.
No, fins are not basically for cooling. You can also use it for heating.
For heat.
Okay.
Okay.
Now figure 4.1 and 4.2 talking about the relevancy. Well, basically that one was just given there to show the monthly, how this monthly function is distributed at different stations. Yeah? That was just to compare the monthly distribution of sunshine at different stations. So I think it's relevant. In that case, we'll be knowing that actually there is more monthly sunshine maybe in Soroti compared to the sunshine distribution that we get from station like Kampala. Well, it may have, but I think it's relevant.
So you can use your calculator.
Okay, the relevance in that case, let me go to the here, okay? What we are saying that, like in this month, when the performance of the system, you want to get heat at high temperature at the top. Basically, if you have it from the bottom, I don't know how you use it for cooking. So if you want to have that in the high temperature at the top, then you have to go it from.
Yes, Dennis, you have to take note of the concerns. So panelists, the discussants, and the public. Okay. Will be useful at the lecture.
Thank you.
Any other questions?
Thank you very much. Dennis, thank you for that work you've done. And as you were mentioning, of course, the cooking is a good thing for help us in cooking and so on. Now, my question is on I'm leaving the solar radiation. Of course, what I did the work is for the tropics, where we know today there will be sunshine, and I think even tomorrow maybe it will be a little cooler, but the sunshine will be there and so on. And I looked at the way you chose the materials. Of course, you say these are a little expensive, and then but they have the good qualities and so on. Then I was thinking about supposing you are going to manufacture those ones for the editorial and maybe some for Europe. Would it be that you would have to manufacture different ones maybe, and then probably those would be more expensive and so on and so on. I wanted to hear that out as we are talking, and in terms of the materials chosen and things, and the way that sunlight is given. And secondly, I was just asking that work you've done, have you made any applications yet? Those are the only questions.
Thank you. The different story, yeah, in that case, that is why we thought of actually incorporating ECM in a bed of rock. In that case, we have a storage. It's relatively a bit expensive, but for those who can afford it, they will go for such system. And for relatively low-income earners, they will go for a bed which is not on the rock side. But that is the relatively big system compared to a small system that we have for. And the publications, actually, part of this work were presented and published as part of the conference done on 3 conference publications were obtained from here, and other publications have been submitted in the same process.
Yes.
Thank you very much, Mr. Okello. I just have 2 or 3 questions. They are brief. One of them is about heat extraction by air blowing. How would you achieve heat extraction in a rural setting? That is one. 2, you mentioned thermal stratification. Well, your thesis will not be read by experts in the field. What do you really mean by stratification, and how was it achieved in your experiment? Just to relay part of what is stratification. And then the last one, I was looking at your thesis. I don't know if you never had any limitations throughout your work. You didn't spell out clearly the limitations of your research method, and possibly in your recommendations how you would mitigate or improve research, or to get rid of the limitations. Those are the 3 points I would like to comment on. Yeah, briefly, on the heat extraction in the rural areas, maybe extraction at night. Think of having a small fan that is powered by solar panel. That is one option we are looking into. But another ways of heat extraction that is reported in the thesis that needs further analysis is to use conducting fringe, highly conducting material where you insert them in the bed. So if you have a highly conducting material within the bed, it will expand the heat to the top plate much easily and faster. The thermal stratification is the difference between the inlet and outlet temperature. How much the difference between the upper section of the bed and the lower part of the bed. If you have a bed where the top part is very hot and very cold down, we say that is very good, highly stratified. In that case, you have a top part and you can really extract heat at the top at high efficiency. Yeah, the limitation of the research, and that one, well, I need to consider it, but I'll take that one.
Yes.
Okay, my questions are based on 2 figures. Figure 4.13 and 4.14. You have to have them on the power calculation. One that has a temperature against the temperature level. No. That one and then the previous one. Yes. So that one, yes, it's presenting the result, but what's the interpretation of that? That's question number 1. Then the next figure. Just for the next figure, please. Just have a question on that. These are plots of both experiment and the model. Clearly, it's a model. Now, I'd like to know what method is used in the model. What method is used in the modeling. And then 2, What's the significance of modeling
Thank you. The interpretation of this is basically showing how, if you have a rock bed, how it will be charged for some given flow rate. That actually mentioned that, because there's a table indicating what the parameters are using. But here, it's showing you now how this bed, the temperature along the bed will behave at different times of charging. Like in this case, if you look, if you just charge this bed for 1 hour, this is a bed of which has a length of 90 centimeters. But you have only the 10 centimeter part that will have received some heat or something, but the rest of the bed will be very cold. Now, as you go after 2 hours, this is how the thermal, this is the profiles that is observed at different lengths of the bed. Showing now that actually, this is actually showing how the heat is, how the bed is getting heated up in time. I don't need to do that. Now, the modeling, in this case we use the Scoons model. That was developed for porous medium. And in the method we use here is to discretize the bed into n section. And what this is actually doing, a total of 90 sections, Please, if you follow from this. Okay, the equation we're basically using at this, okay? To model the bed. And the assumptions we're related to, like in this case, this one is neglected, and we consider, we discuss the bed in n section and look at how the bed will behave in this section. Like in this case, we have the inlet temperature that is known from the incoming air, hot air temperature is known, and we will use the relationship that I presented in the test is to determine the temperature of the rock in that bed and the temperature of air exiting that bed. The temperature of air exiting that bed becomes now the intake, becomes now the inlet temperature to the next section. And this is continued up there, up to the end and repeated several times to what? To determine the temperature at a given time. That is the next question now.
Significance. Why do you not? Why do you not?
Okay. Now we need the model actually in order to now you can use it for sizing our system now. Yeah, exactly.
Why compare the
okay. We need the model in order to work actually now to really determine the behavior of the bed, because we cannot use, since we know that this model is approximated experiment, we cannot use it to look at the behavior of the bed, other than going to experiment all the time using if you change the effect of rock sizes, the model will give you how the bed will perform. Or if you change the air flow rate, it will give you the behavior of the bed at different flow rates. So in that case, we'll be able to determine exactly. Or if you're designing your system, you don't need to work. You can work it and give the design the best parameters for it.
Yes, any other questions? Yes. Yes, you are funny.
I think, in my view, what is very valuable in your work is the experiment, the measurement. You have radiation measurements, and you have the performance measurements of the rock bed, and so on. So that's always a nice contribution, which should be design from the origin and the others build it and make it and just do it. So, so my question is this a good system? We need tracking, span, we need some control, we need installation, and control and heat extraction probably. So now we've done this project work and we have to decide what we do for the future. Is this a good system to continue with? Is this going to be used? That's a difficult question.
Well, that's a difficult question. Since it involves the cost of the system. Now, we have looked at the system, the requirements of the system. We need a concentrator, you need a air transport system, the storage, the pump. But if we are able to design a system that can work, looking at the number of people that can use the system, then basically the cost will go. If you have mass production, basically the cost will be able to go down and the system will be able to work. But this, it will look expensive because we are trying to optimize just to optimize the system. This is expensive material available. But more research is still needed on this.
Yeah, that's one quick thing. You said you did indoor testing. So what was the source of the resin?
Source of what?
The heat. Electrical.
That's part of it.
Okay. Thank you very much, family. We now move on to the public. You have the chance to ask questions and also be answered. Yes.
Thank you, Mr. Okello, for that good presentation. My understanding after listening is that you have actually designed thermal energy storage system, which you can recommend to store heat from. I can give you my example. There is waste heat from an industry that would be released to the environment. That system would actually store that heat. Two, the one you have given, you could actually have heat resulting from heating using solar energy. Now, I wanted to understand how that recommendation for solar energy captures solar energy in your presentation. In which case I would ask, the heat that you used to test this system, was it generated by solar heating? And if it was not, then I want to understand how solar energy and therefore the graph consumption and so on come. Otherwise, I would understand that besides the storage system for thermal energy, which could come from any source. Thank you very much.
Yeah, thank you. That's a very good question and good compliment. Actually, it is actually noted there that the thermal energy storage is used for solar, or we can also use it for industrial waste heat application, or in the fuel cells. Yeah? But here, our main focus is directed towards the solar energy. That's why we look at the radiation distribution of different region and we model it. But the heating, the testing, we really give us indoor testing, trying to see how this bed will behave if you heat it. So that part of constructing the whole system is now going to that will be the next step for the project.
Yes.
Just a really short remark. I think the heat gives you control under conditions, but if you're in Norway during the winter, instead of relaxing, you can do some heat experiments instead of waiting for the sun in the spring. Now, the sun is gone in Norway. If you want to study storage systems, we cannot wait for the spring.
Yes, Professor.
Thank you, Mr. Okello. In your presentation, you mentioned that there are already technologies on the market, similar ones. In fact, I remember watching a program on TV and were described in the similar system. So in your recommendation, I was questioning, you mentioned how you will market this. For example, Makerere is interested in incubating such technologies. Would you interested, what are you going to do that this technology to benefit us compared to those which are already in the market?
Thank you, Professor. The next step actually for this one is basically now to construct the whole system and see now how we test the concentrator. We have to build it and test it now in the whole system, but that was not yet done. And the marketing point will come now after we have developed a complete system. Other technologies that are available, which we have actually seen there, they are associated with a lot of disadvantages. That's why people are really not taking so much, working so much on them. Like the one where you have a concentrator and you need to continue pushing the concentrator. If you were to try such system in the village where somebody needs to go to the garden, do some weeding, and at the same time doing cooking, they will not really be interested in such kind of system. So I think this one that is promoted where you just put your things, you need to something to cook and you can do some other work, people might be interested.
So it's still work to be done.
This is what we done.
Yes.
As far as I know, to my knowledge, there are no systems commercially able to store.
So that's
But the storage is a new element there, so hopefully it can work this much better.
So put it in the incubation and get people to market it. I think that's the point.
Thank you.
Yes, any more questions from the public? If there are no more questions, thank you very much.